In this video, we're going to do some hypothesis testing with the normal distribution. Now, the best way, if you've forgotten it, or if you've seen it before and you're just not quite sure, maybe you have seen it, maybe you got taught it a bit weirdly, whatever the reason. Best way to do it, simple example, okay? Because all the questions are exactly the same, except they just change the numbers, right? They just change the numbers. So here's a question I got from an OCR paper. And we're told that, so what are we looking at? So in this case, we're looking at time spent by customers in a library, okay? And so you're typically told 3 separate bits of information, right? They might group them, doesn't really matter, right? This first blue piece is telling us our mean and standard deviation. So here we're told that our mean is 32.5 and our standard deviation sigma is 8.2. All right, bog standard, great. Then we're told that there's a random sample of 50 customers, so the amount of people is 50, and we see that our sample mean is 34.5. Now remember, our sample mean is just the mean of the sample. And now we're assuming, yes, okay, great, the standard deviation does not change, and now we need to test at a 5% significance level. Okay, now it doesn't actually say in the question, so it's kind of in the background. This is a normal situation, right? As in, we're modeling this with the normal distribution. Okay, so we've got 7 marks here. Test at this significance, so 5% significance level. Okay, these are the parts of the question that you need. And now we launch straight ahead. So there are, 7 marks, 7 steps. Okay, our first step is to write out our null and alternate hypotheses. Okay, if you remember that H0 is the null, so this is what's called the null hypothesis. And H1 is the alternate. Great. Now, what are they in this case? Okay, so H0, our null is what we thought before we did any samples or whatever. So that's this blue bit at the top here. We were told before we did any samples that we thought the mean was 32.5. Okay, now the alternate hypothesis is after we've done a sample, what are we testing right now? There's a subtlety here. So we did a sample and we found that our sample mean was 34.5. Okay. Now we're testing, whether the mean time spent has changed. Okay. When we're testing, hypothesis testing, and I'll come back to this and I'll do the other example, it's either a one-tailed or a two-tailed, okay? Though in this case, it's a two-tailed, okay? So I'll write this in green. So for this question in particular, our alternate hypothesis is whether the mean has changed. Well, if the mean has changed, that means it's not equal to what we thought it was, okay? We don't know if it's high, we don't know if it's lower, we just think it's changed. Now, I'll write it, this is a two-tailed. Okay. Now we also have something called a one-tailed, and I'll do this in red. Now in this case, I'm going to take my one-tailed to be the mean is greater. So the mean specifically has increased, right? And this comes about because we did the sample and the sample mean was bigger than what we thought. Okay. So for the rest of this part, I'll do the two-tailed, then I'll come back and fill in the gaps and what would change if it's a one-tailed, right? Great. So that's the first thing you do. You tell me your H0 and your H1. Okay. Second thing, if someone's reading this, right, and this is why they stress, anyone should stress, okay, this second point, right, is if I'm reading this, I don't you haven't told me what mu is, right? I know it's a mean of something, but I don't know what it is. So we need to define it. So we need to go where mu is, in this case, the mean time spent by, oh, that's not how you spell customers. Customers in the library. Great. Okay, that's the second thing we do. We then say, okay, what is mu? So far, so good. That's 2 marks, and I haven't really done much maths. Always like when that happens. Right. And yep, okay. Now we have to, unfortunately, do some maths. So, x is going to be the time spent by a customer. Okay. X is going to be my random variable for the time spent by a customer in the library. Okay. And I know it's going to be normally distributed with the mean 32.5, because we were told that, and a standard deviation of 8.2. So that's 8.2 squared there, because remember, that's the variance. Okay. Now, I also need my sample distribution. So my sample mean x bar. It's going to have a normal distribution with a mean of 32.5. Now, there's a formula that I will write down at the top here, right? That if we have a random variable distributed normally mean mu variance sigma squared, then a sample will have the same mean, still normally distributed, but with a slightly different variance, okay? And we just need this formula in our answer. You don't need to understand where it comes from or whatever. You can just take it as, oh, great, someone's made my life easier. Don't have to don't have to worry about that too much. Just use it, right? Well, our n in this case I've written is 50. And now I've got my 2 distributions. Okay, so I've written down my 2 distributions. Now, I need to find out, and this is the whole idea behind a hypothesis test, is I need to find out if me picking a sample of 50 customers and getting a sample mean that is 34.5 is likely or not. Because there's some randomness associated with that. I could have picked customers who really liked the library and were staying there for ages, and hence got my higher mean. I'm not quite sure, right? Now, the way I'm going to do this is I want to find the probability that my sample mean, okay, is bigger than what I've observed, okay? So if I were to draw this as a little graph, so here I am drawing x bar, okay? Now this is my mean. So my mean is what, 32.5? And let's say this point here is 34.5. Okay, so I'm looking for everything to the right. Okay, this statement is me asking, right, is my sample mean, what's the chances my sample mean was 34.5 or anything bigger, right? What if it's 35, 37, whatever. Okay, now when you get to this stage, it's not that difficult. We're going to plug in, and I'm going to write exactly what I'm plugging into the calculator. So we're going to go menu, and we're going to go into whatever distribution you've got for a normal distribution. Okay. And for our lower, we're going to plug in 34.5. Our upper, you could just put a load of 9s. It doesn't really matter, as long as you make this big enough. Our standard deviation is 82.5, but hang on. We need to divide it by, we divided the variance by 50, so our standard deviation is now divided by root 50. and our mean is 32.5. So plugging this information in, I get the probability x bar bigger than 34.5 is equal to, so let's just plug it in, 34.5, load of 9s, 8.2 divided by root 50, and 32.5. We get 0.0423 to 3 significant figures. Okay. Now, why on earth have I calculated this? Okay, what does this mean? It's literally just the area past 34.5 on our distribution. Okay. Now, we're nearly there. Okay. Now, this is where the one-tailed or two-tailed comes in. Because it's a two-tailed test, right? We're going to compare this number not to our 5%. So our 5% was our significance level. We're not going to compare it to 5%. Because we're in a two-tailed, we're going to compare it to 2.5%. Okay, which written as a decimal, let's see if I can get the right number of zeros. So that's a 10, is that. Okay. The reason I'll come back to in a minute when I show you the difference between the one-tailed, but for now, just take it as if you see two-tailed or if you're doing a two-tailed test, look at your significance and half it, right? Now, hopefully you can see that our probability, so our probability that x bar was bigger than 34.5, which is 0.0423, is bigger than our significance level. Okay. Now, because the probability that we just calculated is bigger, what this tells us, and you have to phrase it like this, okay? Okay. This tells us that the chances of us seeing something bigger than 34.5, right, is bigger than our significance level. Well, half of it, okay? So in this scenario, we say that there's, well, we're not going to reject H0. We're saying, okay, that our alternate hypothesis, which is mu is not equal to 32.5, based on seeing a sample mean of 34.5, could have probably happened, right? That's what's going on here. Oh yeah, and this is, yeah, okay, this is what's going on here, okay? You compare it here, and we're like, okay, if it's bigger than the significance level, you do not reject it. So that, I'm going to write that here as number 6, right? So we do not reject H0 because it's bigger. Okay. Now, this is our conclusion, but we're not quite done. We also need to link it back to the question. So, big deal. We've just said do not reject H0. Okay. What does that actually mean? So that means, right, that we think the mean is still 32.5. Okay. So the way you write this in silly stats words is there is, now can I spell it right? Insufficient evidence to reject H0, the mean, and then what actually is it? Time spent by customers is, what is it? 32.5, right? Okay. Now, oh, I've missed it out. Here, you just add the 5. So whatever significance level you've tested, you write that just here, right? Great. Now, it's not too strenuous. Now, you say the words do not reject, okay? You won't get marked down if you say accept, because that's the same as do not reject. There's 2 negations, it's going to be accept, right? But when you're talking stats, okay, you can think about it as, right, I will give you £1 million, okay, if your guess of the mean being 32.5 is correct. However, if it's not 32.5, you have to pay me £1 million. Okay, those are pretty big stakes, right? Now, with the information at hand, we do not have enough information for me to say that H0 is correct, right? And in the scenario I've just presented, you don't have, and you wouldn't probably feel comfortable enough to bet essentially everything you own on the mean being 32.5, okay? There's not enough evidence, right? So, as statisticians that we are, okay, we are not saying that we agree with H0. We're saying that there's not enough evidence to discard it, right? With what we've got, it's our best guess, okay? That's why you see a big stress on saying reject or do not reject and never accept, okay? Now, I alluded to up here, there are 2 ways to do it, right? So we've just done a 2-tailed. Now let's look at how it differs for a 1-tailed. So for a 1-tailed, step 2 is the same, step 3 is the same, step 4 is the same, blah, 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 blah. Now, step 5, okay? For a 1-tailed even, so I'll draw a little. For a 1-tailed, we're going to compare it to the significance level, okay? Just the significance level. We're not halving it or anything. We're not doing anything funky, okay? So if we were testing with a 1-tailed test, we'd see that our probability 0.0423 is actually less than 0.05. Now, this is saying that the chances that we see what we've observed, which is 34.5, or anything higher, is less than our significance level. Okay, so it's quite unlikely. You can think about the significance level as how likely it is for this to happen in a vague sort of sense, right? If our number that we get is below our significance level, then it probably means that it's quite unlikely for us to see what we've seen. Okay, which leads us rejecting H0, okay? Compared to when it was a 2-tailed and we saw that the number was bigger, we didn't, because the number was bigger than our significance. Now, where is this coming from? So I'm going to draw another picture here, right? Where is this coming from? And why are there differences, and why do you care, right? So this is going to be our distribution, probably badly drawn. Oh, that's not too bad, right? This is our distribution, and it's distributed like this, 82.5. There we go. Okay, great. Our mean is centered there. Okay, now, so the green is going to be a 2-tailed. Okay, now, and then the red's going to be a 1-tailed. Okay, now the easiest one in my mind to get around is just the 1-tailed. Okay, so remember our 1-tailed is that the mu is bigger than 34.5. Okay, so I'm going to get, oh no, not 34, 32, sorry. There we go, right. So we observed here is going to be 34.5. So this is our sample mean that we observed, okay? Now, when we're testing, and I'll use the example 5%, right? This is our 5% significance level, okay? What that is saying is, okay, we're in a 1-tailed test, and I'm going to look at the probability that my sample mean is bigger than this 34.5, okay? So that's this area. Now, the significance level is saying that if this area, okay, this area is less than 0.05, okay, so there's less than 5% of the data is on this tail, hence the tailed, right, then it's quite unlikely that we saw what we saw, which was 34.5 or higher, right? Okay. So this is completely fine, right? We're just looking at our significance level and accepting it, right? However, on a two-tailed test, remember that's not equal to 32.5. Well, that could also be represented here by this tail. So I'll color it green as well, right? However, okay, that's this case. But we've also said it could be lower. Okay. So what's actually going on is, well, if I make this look symmetric, so I'll do it in blue. Actually, no, I'll do it. Yeah, there we go. Right. If I make this look symmetric, so what have I just done here? I have picked a point here that is the same distance away from the mean as 34.5. So this would be 30.5, right? And now I'm considering this area as well. Okay. So let's call this area 1 and this one area 2. Okay. So now I'm looking at two areas. Okay. Because I want to see, okay, if the chances of me being greater than or equal to 34.5, so this extreme, A2's extreme, or it being less than, okay, now, because I've got a little bit of symmetry, right, that would be less than 30.5, okay? This is for a two-tailed, okay? Now, the 5% is the area that we're interested in, but now we've got two areas, okay? Now, because we're working with a normal distribution, what you'll actually find is, because it's symmetric, both of these areas are the same, okay? So both of our areas are the same. So let's call them now, just each one is A, right? So our total area that I've shaded in green is 2A. Now we're going to apply this same reasoning. If the area is less than, so this is our area, if this is less than 0.05, then we are saying that, okay, it's unlikely that we saw something as extreme as what we've just seen, okay? In this case, sample mean of 34.5 or greater. But secretly, we're thinking also it could have been on the other end, right? Could have been on the other tail, okay? Now, if you look at this, you might go, oh, wait, I could divide by 2. Hang on a minute, okay? This A represents this tail, and we're looking, if it's less than, oh, look, I've halved the significance. That's why you halve the significance, right? It's useful to remember why you're halving it. If you see a two-tailed, then you need to half it, right? It's useful to remember this, but it's not essential. If you're okay with just halving it and not worrying about it, that's fine. But if you're someone who maybe needs a bit of an explanation just to make it stick, right? Here it is. Two-tailed, both ends, and they're the same area both ends, so I need to halve my significance. One-tailed, just one end, don't have to do anything. Yeah, great. I think that's a good place to stop.